All right, so we're now moving into chapter 10, which is on, we've been doing hypothesis tests now since chapter 7, which was the Z test, which is talked about right here. Um, and then in chapter 9, we did these two right here. We did the paired samples t-test, or which is also known as the repeated measures t-test or within subjects t-test. And the one sample t-test we also did in chapter 9. Um, and it mentions here every inferential statistic that we've calculated so far, every hypothesis test we've done has involved just a single sample mean. That's particularly obvious for one sample t-test and the z-test. So I put in parentheses here for z-test, I put in parentheses one sample because usually it's not called one sample z-test, but that really is what it is. The z-test and the one sample t-test are very, very similar. In both cases, you are comparing a sample mean to a population mean. That is what the significance test tells you, whether the sample mean and population mean are significantly different from each other. So you have only a single sample mean for these one sample tests, whether it's one sample t in which you do not know the population standard deviation, and the one sample z test in which you do know the population standard deviation. In both cases, you're comparing a sample mean to a population mean. And I was looking ahead to test 4, and I feel like because of one of the questions, I should mention that if you have the option to choose between these two types of tests, the one that you would prefer would be the z-test. It's statistically more powerful. And in general, if you can do a hypothesis test using the population information, using the population standard deviation, that's considered better than a t-test in which you have to use the sample standard deviation instead. In general, if you know information about the population, like you do in the z-test, but not the t-test, it is better to use the population information. So z-test, one sample z-test, if possible, is preferred over the one sample t-test. But anyway, what I'm arguing here, or what I'm showing you in the slide, is that everything we've done so far has just involved a single sample mean. Very obvious for the one sample t-test and one sample z-test. It's kind of implied by their names, but it's also true for the paired samples t-test. We calculated the single sample mean, which we called M sub D. That D stands for difference score. And we compared this M sub D, the mean difference score, to a population mean. But what that population mean represented was what we would expect the difference score to be if there was no significant effect. And so I mentioned last time that when we're doing a paired samples t-test, that is within subjects t-test, repeated measures t-test, the null hypothesis is always that the mu sub d, the population difference score, will always be 0. That is always the case with the paired samples t-test. This will always be 0. But for paired samples t-test, once again, we have a single sample mean. But it's important to remember that what this one sample mean represents is the difference represents the difference in means between two conditions. But we're doing that by subtracting one condition from the other, and we get a difference between those two conditions. So we get like a single number which represents the difference between two conditions. And that's what this M sub D stands for. So when we're doing all of these, we have a single sample mean, M, that we are comparing to a population mean, mu. That's going to change today with the independent samples t-test. In my view, we're now starting to get into some very practical statistical tests. Out of all of these so far, the only one that's like highly used, the paired samples t-test, is very common in actual practice, whereas one sample t-test is not very, it does happen. I've actually published one study that had a couple of these in it, but it's pretty rare. One sample t-tests are not very common. Z-tests are not very common. At least in my field, paired sample t-tests are pretty common, actually. And independent samples t-tests, which we're going to learn in this chapter, are definitely common. I'd say so far, independent samples t-test and paired samples t-tests are the two most practical type of t-test or practical type of hypothesis test, inferential statistic, that we will have learned so far. So independent samples t-test, what does it do? It compares two sample means to each other. So instead of comparing a single sample mean to a population mean, it's possible to think of the independent samples t-test as just comparing one sample mean to a second sample mean. Here, I'm just reminding you that one unfortunate reality about these tests is that they're called many different things. And so part of the skill of statistics is kind of remembering that a given test can be called multiple things. So independent samples t-test, also called independent measures t-test, or between subjects t-test. Or a two sample t-test, to contrast it with, in previous slide I showed you the one sample t and the one sample z. Those have one sample, obviously. The two sample t-test has two sample means, and we're comparing those two sample means to each other. From now on, I think we'll probably mostly, like for these independent samples t-test problems, my plan is to only ask you questions where there would be two-tailed tests. And so remember, a two-tailed test is when you have a critical region on the right and a critical region on the left. A one-tailed test would be the critical regions on the right or the critical regions on the left. And the reason we're going to focus on two-tailed tests is just because in actual practice and in real life, two-tailed tests are way more common than one-tailed tests. I don't think I've ever done a one-tailed test in my career, but I've done many two-tailed tests. So two-tailed tests are just used way more often. And so we're going to focus moving forward on two-tailed tests. You know what one-tailed tests are. You've done some of them. But moving forward, we're going to focus on two-tailed tests because they're just much more practical for real life. So the null hypothesis for an independent samples t-test is shown right here. It's kind of two ways to repeat it, or two ways to state it. Mu1 equals mu2. In other words, this 1 and 2, like the mean of sample 1 is the same as the mean of sample 2. Another way of saying that is that if you take the one mean minus the other, the difference should be 0. This is the null hypothesis. If there's no treatment effect, if there's no differences between our means, that means that the means are approximately the same number. And if you subtract two numbers that are approximately the same from each other, you're going to get a number which is close to 0. So the null hypothesis is mu1 minus mu2 equals 0, or mu1 equals mu2. These are mathematically identical. They're, just algebraic manipulations. These are the identical statements. The research hypothesis, stating that there is an effect, says, probably not surprisingly, mean 1 does not equal mean 2. This is clearly implying a two-tailed test because we're just using the does not equal sign, which implies that mu2 could be greater than mu1, or mu1 could be greater than mu2. Either of those would satisfy this statement right here. And once again, this is the equivalent way of writing it. Mu1 minus mu2 does not equal 0. Another important difference between this t-test compared to the t-tests and all hypothesis tests we've done before is that the degrees of freedom now equals n minus 2. So you take the total sample size, the total amount of people in your study, you take that number and you subtract 2, and that gives you the degrees of freedom that you will then use to look up your t-table to find the critical t-value that will then mark those boundaries into the rejection region or the critical region. And so you'll be using that degrees of freedom right there to look up the critical regions on the t-table. Any questions or comments so far? Yeah, so here's looking at all of the t equations that we've dealt with so far. Here's the one sample t-test. Notice how it has one sample mean comparing it to the population mean. Then we have estimated standard error down there. For the repeated measures t-test, same basic deal. We have the sample mean, though the sample mean represents a different score. It represents the difference in means between two conditions, minus the mu sub d. But remember, this number always equals 0. So you basically never really have to worry about this because it's just always 0. Dividing once again by estimated standard error. And then finally, here is the t equation for what we're going to be learning in chapter 10, the independent samples t-test. We have the two sample means here, so you can see them. It's like I called it earlier, kind of the two sample t-test, and you can see the two sample means right here. The good news, once again, is that because of the null hypothesis, this part right here is going to equal 0. And I really want to emphasize that. Mu1 minus mu2 equals 0 according to the null hypothesis. Mu1 minus mu2, that's the exact statement that came from the null hypothesis. This equals 0, so just like you didn't have to really do any calculations involving mu sub d, that just falls away because it just turns to 0. The same thing is true for independent samples t. So really all you have to care about in the numerator is the difference between your two sample means. That's going to be what the numerator is. And then probably the most tricky aspect of the independent samples t-test is the estimated standard error, which is calculated in a much different way than it's been calculated before. You do not need, I'm going to show you how to calculate this weird way of this, I don't want to call it weird, but I'm going to show you how to calculate estimated standard error for independent samples t-test. There is only, I looked ahead to the test, there's no actual calculations where you have to do estimated standard error for an independent samples t-test, though there is one or two conceptual questions about estimated standard error. So you need to kind of understand this, though you do not necessarily need to know how to calculate this for test number 4. So all I'm showing you here is that this formula, which is kind of big and intimidating, because mu1 minus mu2 of the null hypothesis, this equals 0. Really, you could think of this formula for all practical purposes. This is it right here. The differences between our two sample means divided by estimated standard error. And I still need to show you how to calculate estimated standard error, this thing right here. So here's where I show you how to calculate. Here's where I show you some of the formulas for calculating estimated standard error. So right here, s divided by the square root of n, this is the way we've been, for the most part, calculating estimated standard error. Up till now, you take the standard deviation divided by the square root of n. A mathematically equivalent thing is taking the square root of s squared. S squared is variance divided by n. These are just algebraic, or not even algebra. These are just mathematically equivalent statements. You get the same answer, so this is estimated standard error, and this is also estimated. These two things give you the exact same number when you plug in different numbers. You plug in the standard deviation divided by the square root of n, that gives you the same number as taking variance divided by n and then taking the square root of that number. The formula that we're working toward down here, this formula down here, is how you calculate estimated standard error, for chapter 10. This formula right here uses this idea right here. So this is kind of a new idea. It's a slight new idea. It's mathematically equivalent to this, but we've never actually used this way of calculating things. But this is basically the logic, or this is the basic structure of this equation down here, is using this idea of the variance divided by n, take the square root of that, and that gives you estimated standard error. But in order to calculate estimated standard error in chapter 10, we have to know this thing called pooled variance, which is what this is right here. You take sum of squares 1 plus sum of squares 2 and divide by degrees of freedom 1 plus degrees of freedom 2. I'll definitely show you an example of how to do this on a subsequent slide. Make this a little bit less abstract like it is there. Yeah, I will show you how to do that. And then we will use this number, this thing right here, the variance s squared, but it's pooled variance. That's what the P stands for. This number, after you calculate it, is used, you kind of plug it into this formula down here. You can see pooled variance right there. and then you'll plug in the exact same number right there, pooled variance. You divide each one by the sample size of condition 1, divided by that right here, divided by the sample size of condition 2. You add up those two ratios, then you take the square root, and that's how you get estimated standard error for an independent samples t-test. Before we move along, I want to just give like a picture to kind of explain the type of situations in which we'd use an independent samples t-test compared to a paired samples t-test. Right here is a between subjects design. This is where you would use an independent measures t-test. Right here is a within subjects design. This is where you would use a paired samples t-test, a repeated measures t-test, a within subjects t-test for this data set. For this one, between subjects t-test, independent samples t-test, independent measures t-test. Remember, each one of these has multiple names. Before we move along, though, I want someone to remind me, this is a between subjects design shown here. How do we know, like, what is the giveaway? This is a between subjects design, but what about what I'm circling here indicates that this is a between subjects design? How do we know by looking at this that it is, in fact, a between subjects design? Anyone? I feel like we have talked about this stuff before, so I really want us to try and remember this. This is a between subjects design. This is a within subjects design. What is the essential difference between these two data sets right here?
In the between groups design, each participant is assigned to only one condition.
Perfect. That's exactly right. And can you contrast that, please, with the within subjects design? Can you explain?
In the within subjects, each participant has multiple conditions. They have the no coffee and the coffee.
Exactly. Good. That was perfect. So yes, between subject design, you can see participant 1 is only in the no coffee condition. Participant 7 is only in the coffee condition. Participant 6 is only in the no coffee. Participant 12 is only in the coffee. But if you go to with the within subjects design, you can see participant 1, you get a score for this person in no coffee, and you also get a score for this person in coffee. So this is within subjects design right here. This is when you use paired samples t-test, which is what we learned in chapter 9. In this chapter, we're doing this thing right here, where it's between subjects factor. Each participant, you get a score in only one of the conditions. Independent samples t-test, also known as independent measures t-test, or between subjects t-test. Good. Okay, so here is like an example where giving you, I think I have, this is like a beginning example for pooled variance. And then I actually have another calculation where I'll calculate pooled variance in a second. So what's really important about this, and there was, when I looked at the old test that they've used for this class over the weekend, there was definitely a question which is getting to this thing about sample size, which I'm trying to illustrate. I think it says in the notes. I want to make sure it does before I move on. Yeah, it says right here, pooled variance is more strongly influenced by the sample with larger N. And there's a question on the test, which is basically getting at that. So it's one of the, I told you in the test, you're not going to actually have to calculate pooled variance with like a calculation, but you need to know some conceptual things about it. And one of the things that you need to understand is that pooled variance is more strongly influenced by the sample with larger N, which I've highlighted in the text in the notes right there. And the reason why this matters is because you got to really think about the difference between a within subjects factor compared to a between subjects factor. And a within subjects factor, each participant is in both conditions. So you're always going to have an equal amount of scores in condition 1 compared to an equal amount of scores in condition 2 when you're doing a within subjects design. That is a paired samples t-test. You get 2 scores for each person, one in condition 1 and one in condition 2. So you're always going to have the same amount of scores. This is condition 1, this is condition 2. You're always going to have 2 scores going down the list. One for condition 1, one for condition 2, one for condition 1, one for each participant. You're always going to have 2 scores. In a between subjects design or an independent samples t-test, that's not always the case. Sometimes you'll have like 7 scores in condition 1, but you'll have like 12 scores in condition 2. So things are no longer equal. You don't have necessarily the same amount of scores, the same amount of data in your 2 conditions. We still need to calculate estimated standard error. We still need to calculate standard deviation in order to calculate estimated standard error. But because the sample sizes can be different, we need a different strategy for calculating estimated standard error and standard deviation, or variance in this case, which is used to calculate estimated standard error. And so that's the deal with pooled variance right here. So I've given an example. So we have this study. Condition 1 only has 3 people, which is a very small sample size, but it's just a teaching example. And then the sum of squares is 20. Remember, sum of squares is part of the variance equation. The sum of squares is when you take each x value minus the mean of that condition, and then you square it, and you add those numbers up for all of the x values in that condition. That's what sum of squares is. Each x value minus the mean squared, and then you add up all of those numbers. That's what sum of squares is. Adding up all of the squared different scores is what sum of squares is. So in this condition, we have 3 people and the sum of squares. When we add up those 3 things, the 3 squared different scores, we would get 20. In condition 2, there's 9 people. And when we add up the 9 squared different scores, we got 48. So the sum of squares for this condition is 48. So this is a situation in which the sample size is not equal. 3 and 9 are different. There's a lot of scores in condition 2, relatively less in condition 1. And so here, once again, is the pooled variance equation. And here I'm just plugging in these numbers right here to get our pooled variance. So 20 is that number right there, sum of squares 1, plus 48, this number right here, sum of squares 2 for condition 2, 20 plus 48, 20 plus 48, dividing by 2 plus 8. So 2 comes from the fact that we're taking 3 minus 1, degrees of freedom 1, 3 minus 1 equals 2. And this 8 comes from the fact that we're taking 9 minus 1, which gives us 8. And when you do the math, you get 68 divided by 10, which equals a pooled variance of 6.8. So as I said, you're not going to be having to calculate, to my memory, you're not going to be having to calculate this on test 4. But there is some conceptual questions about it. One of the conceptual questions has to do with the fact that pooled variance is weighted so that the sample size, this equation right here, is weighted so that the condition that has a bigger sample size is going to have a more dramatic influence on what the pooled variance is. And you can see that by looking here. In order to understand that, you have to look over here. What I've done over here is I've calculated the variance for each of these conditions by itself. So this is the pooled variance, which kind of combines the variance of those 2 conditions together. What I've done here is this is the variance for condition 1. This over here is the variance for condition 2. And I've done that by taking the sum of squares divided by the degrees of freedom, which for condition 1 equals 10. 48 divided by 8 for condition 2, this equals 6. And if you notice, the pooled variance that we finally calculated is closer to this number right here. It's closer to 6. 6.8 is closer to 6. And the reason that worked out this way is because this right here, this is the condition that has a bigger sample size. So when you calculate pooled variance, the number that you get will be closer to the variance of the individual condition that has a bigger sample size. A neat little mathematical fact is if the sample sizes are equal, then you could take the average of the variance of condition 1 and the average of the variance of condition 2. So you add up the variance of condition 1 plus the variance of condition 2. You add those two things up, divide by 2. If the sample size are equal, the average of the variance for the two conditions will equal exactly the pooled variance. But if the sample sizes are different, as they are here, the pooled variance is going to be closer in value to the condition that has a bigger sample size. 6.8 is closer to 6. And that's the sample that had a sample size of 9. It's closer to 6 than it is to 10. It's relatively closer to 6 than 10. Questions or comments about this example of pooled variance? Okay, so I guess this is just basically, actually, yeah, there's really not too much to talk about here. This is not a bad thing to have on the slides for you guys to review later. I guess the one thing which is important to mention here, which is the same as the other T's, is that we're going to calculate a T value for independent samples t-test. And just like when we were calculating Z back in chapter 7 and when we were calculating T in chapter 9, the further the test statistic gets from 0, the more likely we are to conclude that we have a significant effect. The further the test statistic gets from 0, the more likely we are to reject the null hypothesis. It is important to notice now, though, that when we are going to be looking up our t-table, the degrees of freedom, and I'll show you an example of this, that we're going to be using is now n-2. That 2 you can think of, instead of n-1, which we did when we had one sample mean, now that we have two sample means, the degrees of freedom that we look up on our t-table with is n-2. 2 because we have two sample means. So here is a practice problem, an entire, this is calculating T from scratch for a data set that I've made up completely right here. So every single possible thing we could calculate is calculated right here for this data set right here. So this is a made up data set, condition 1, condition 2, the mean of condition 1 is 6, the mean of condition 2 is 7. The variance of condition 1 is 0.2 repeating. The variance of condition 2 is 0.8 repeating. The sample size of condition 1 is 10. The sample size of condition 2 is 10. The overall sample size here is 20. So that means the degrees of freedom for this one is going to be 18. The total sample size, in this case 20, the total amount of people, minus 2, that's 18. So now we need to go ahead and calculate. The first thing we have to work towards calculating is pooled variance. And then we'll use pooled variance to calculate estimated standard error. So here's pooled variance, here's estimated standard error. And then we use that estimated standard error, we'll plug that into the T equation that will give us our T value. So let's kind of start here. And remember, in order to calculate pooled variance, here's the equation for pooled variance filled in with numbers. This number right here, 2, that's sum of squares 1. This number 8, this is sum of squares 2, and that's what I'm calculating right here. Sum of squares 1, sum of squares 2. So I'll walk you through how we got these things right here in a second. Just kind of general structure. Sum of squares 1 plus sum of squares 2 divided by the degrees of freedom for condition 1, which is 10 minus 1, plus the degrees of freedom for condition 2, which is 10 minus 1, which is 9. By the way, which equals the total degrees of freedom, which I just mentioned. The total sample size 20 minus 2 is 18, and that's actually what the denominator is. You could think of the denominator as just the total sample size minus 2, or just the overall degrees of freedom. So I plugged the numbers in here for the pooled variance, but let's make sure that we understand how we got all these numbers. So right here, this is 2. This is sum of squares 1. The way we do that is we calculate the sum of squares for condition 1. So we get 5. This is the first x value right there, 5 minus 6. The 6 comes from the fact that the sample mean for condition 1 is 6. 5 minus 6 equals negative 1. Negative 1 squared is just positive 1. Moving to the next one, 7, which is right here, minus 6, which is still the sample means, So the next x value minus the sample mean, that equals 1. 1 squared is still 1. And then you notice that all the rest of the x values are the same number, 6, 6, 6. And then, so you take for the third x value 6 minus the sample mean, which is 6, that equals 0. 0 squared is 0. And you know that all of the rest of these are just going to be 0, 0, 0, 0, 0, 0, because 6 minus 6 is going to be 0. And so when you add up the event, I didn't show all 10 of them because that would be a lot of work, and because the last 7 are going to be the exact same thing, that's right here. But when you add up all of these numbers, you get 2. So the sum of squares of condition 1 is this number here, 2. Let's do the same thing for condition 2. There's the number 5. So there's 5 right there. Minus 7. The 7 comes from the fact that the mean of condition 2 is 7. 5 minus 7 equals 2. Minus 2. Minus 2 squared equals 4. And then the next one, 9. There's number 9 right there. Minus 7, which once again is the sample mean. 9 minus 7 equals 2. 2 squared equals 4. Then we're going to the third one now. So 7, which is right here, minus the sample mean for that condition, which is 7. 7 minus 7 equals 0. 0 squared equals 0. And the last 7 or 8 numbers here, the square difference score will be 0. So I didn't write all those down. And so when you add all these up down here for condition 2, you get 8. 4 plus a whole bunch of zeros equals 8. And so that's where this number right here comes from, 8. 2 plus 8 equals 10. And then down at the bottom, the total sample size is 20 minus 2 equals 18. Or another way of calculating that would be taking the degrees of freedom for each condition individually. So 10 minus 1 equals 9. 10 minus 1 equals 9, and then add those two things, which equals 18. And then when you just work out the math, you get 0.5 repeating, which I've rounded with the 6 right here, 0.555556. That technically, I'm pretty sure it's just 0.5 repeating for infinity. So this is the pooled variance. One of the things that I want to point out, which I mentioned last time, which is kind of cool about the pooled variance, is that if the sample size is equal, there's a shortcut way of calculating the pooled variance. If you know the variance for condition 1 and you know the variance for condition 2, the alternative way of calculating this number is just average these two numbers right here together. If you add up 0.2 repeating plus 0.8 repeating and then divide by 2, you get this exact number right here. So this pooled variance equation, it's good to know this, though. If the sample sizes are equal, you can always just take the average of the individual variances, and that will equal the pooled variance. But I'll remind you, if the sample sizes are not equal, then averaging these two numbers doesn't work, in which case you have to use the pooled variance equation to calculate pooled variance. So once we know pooled variance, then we use that number, we insert it into this equation that I showed you earlier. I think I want to show you again. Where is it? Right here. This is the equation we're plugging things in. I'll remind you, this is derived from this idea right here. The variance divided by n, then take the square root of that number. That gives you the estimated standard error. This is, we're trying to calculate the estimated standard error, and it's kind of using the same structure. The variance divided by n. We're using the pooled variance divided by n, and we're doing it twice because we have two samples, and we're adding those two numbers together. And then we're taking the square root of that, just like we did up here. So this is structurally similar to this right here, but we're using pooled variance here, and we're adding these things together. And so here's the estimated standard error with the pooled variance divided by 10. That is the sample size of condition 1, plus the pooled variance divided by 10. But this 10 right here is the sample size of condition 2. And then you add those two numbers together, those two ratios, you add them together, you take the square root of that, and you get 0.3 repeating. This is our estimated standard error right there. And then just like always, estimated standard error goes in the denominator of our t equation. And you can see it right there, a bunch of 3s, 0.3333s, and the denominator of our t equation. The numerator is just 6 minus 7. 6 is the sample mean of condition 1. 7 is the sample mean of condition 2. That equals minus 1. minus 1 divided by 1/3, or minus 1 divided by 0.3 repeating, gives you simply a nice round number. -3 is our t-value here. So maybe it's a decent idea, unless I do it here. Yeah, maybe now's a decent idea, a decent time to go ahead and look this up on our t-table to do the hypothesis test to determine whether we have a significant effect or not. So let's go ahead and do that. So our degrees of freedom, I mentioned, the sample size is 20. For an independent sample t-test, you take 20, you take the sample size minus 2. So our degrees of freedom is 18. Let's go ahead and look up our critical t-value. So you look up degrees of freedom, which is 18, right here. And then we will assume two-tailed tests with alpha equals 0.05. So two tails, alpha equals 0.05, go down to where that intersects with 18. Our critical t-value is 2.101. But it's a two-tailed test, so that means that our critical t-value is plus or minus 2.101. 2.101 plus or minus 2.101 is our critical t. When we calculated our t, we got -3. So the question I have is this, I want you to think about it, is this in the rejection region, the critical region? Yes or no? Anyone know? This -3 is in the critical region. It is in the rejection region. -3 is far to the left. Our critical region, our critical boundary on the left side is -2.101. -3 is well beyond that. Therefore, we would reject the null hypothesis. -3 is to the left of our critical value, -2.101. It's definitely in the critical region. And so we reject the null hypothesis. We would conclude that these two sample means 6 and 7 are significantly different from each other. Any questions or comments about calculating t or looking up the critical t on the t-table or making a decision regarding the hypothesis test? All right. So when I was looking ahead to the test, I noticed that for your test, the thing that you're actually going to have to do is use SPSS. There's going to be a written portion again. At least that's the way it's been in the past tests. And you're going to actually have to use SPSS to perform a t-test. So you're not going to be, as we're moving forward in the class, you're going to be doing less hand calculations, and you're going to be using SPSS to help you perform these same calculations. But it's always nice when you can see that what you perform by hand is the same as what SPSS gives you. So what I've done here is the exact same t-test. We just performed an independent samples t-test by hand. Now we're gonna, over the weekend, I performed for that exact same data set, I logged into the SPSS from the virtual lab from KU, and I analyzed the data using SPSS. And we're going to do the same. I'm going to kind of walk you through what I did here and explain what's going on. And I believe for homework 5, you actually will have to do one of these. So pay special attention. This will help you for homework 5. So a couple things I need to point out. This is the data editor side of SPSS. So we have 2 columns. This is the scores column. And it has all 20 of the scores. So remember, our sample size was 20. And all 20 of those scores they're all lined in this one column. So I really want to emphasize this. Where'd it go? Yeah. So the way to think about this is it's like I copied and pasted this entire column, but I pasted it below this column right here. So I took these 10 values right here, copied it, and then I pasted it below these 10 values right here. That's basically the way it works. Here is like condition 1 right here. And then I copied and pasted condition 2 so that it's below condition 1. So condition 1 and condition 2 are all in one column. That's how you do an independent samples t-test. And then you have to do something that I don't think we've done much before called dummy coding. So this is the scores column and this is the dummy code column. And basically what the dummy code column does, you just manually will type in numbers. And each number helps SPSS to categorize each score as either belonging to condition 1 or belonging to condition 2. And so you can see these first 10 scores, which all belong to condition 1, they're basically given the dummy code label of 1. And all these 10 scores down here that are part of condition 2, they are all labeled with number 2 right here to indicate that these belong to condition 2. So you need to do all of these things to do an independent samples t-test in SPSS. You need to have a column of all of the scores all lined up into a single column. And then next to it, you need to have another column, but in this column, it's kind of naming each individual score. It's allowing SPSS to know each score, which of those 2 conditions does it belong to? Is it in condition 1 or condition 2? And you can see those numbers right there. So this is how you set. Any questions about how I set up this stuff in SPSS? All right, so let's run the independent samples t-test in SPSS. So it's a screenshot. I don't actually have SPSS open, but you can see I was using Citrix, which is what you guys all have access to via KU. So you're going to click Analyze at the top, and then Compare Means, and then you choose Independent Samples t-test, which is what we've been talking about. Analyze, Compare Means, Independent Samples t-test. And you can see some of the other choices are some of our things we've already worked with. One sample t-test we've already worked with. Paired samples t-test we've already worked with. But here we're going to be working with independent samples t-test. That's what we're going to choose here. So you would click on that. Then you would move to this next. You're going to get the next thing you would see will be like this. I've already moved over for the screenshot. Let's move this thing. So after you click independent samples t-test, you're going to see something like this. I've already moved over all the stuff. So when you start, you're going to see the word scores over here. You're going to have to move it over to the test variable box. You're going to see the dummy code. It's going to be over here too. You have to move dummy code over to the grouping variable box. When you do that, these numbers 1 and 2 do not appear there. I think they're question marks. What you're going to have to, so there'll be question mark. When you move dummy code over here, these are still going to be question marks. You need to press define groups. And then you can see that's what I've done here. When you press define groups, you need to physically write in the number 1 for group 1, and you need to physically write in the number 2 for group 2, and then you press continue, and then this will close, and then it will be exactly like this. This is how things will look. And then once things look like this, you can just press OK right here, and then you can run the independent samples t-test, and you'll get, I think that's the last thing, then you get output. That's all you have to do to run the independent samples t-test. And then I think we got the output here. Yeah, here's the output. Once again, it's a screenshot. So you can see the means of our 2 conditions. So there's the mean of condition 1, 6. The mean of condition 2 is 7. These are just the basic descriptive statistics. The stuff that you really need to care about, the stuff that you'll really be working a lot with, is right here. And so this t-value, and I've circled them, well, I've rectangled them in red. So the t-value -3, please note, that's exactly what we calculated when we got it by hand. The degrees of freedom is 18. That's what we knew that when we looked that up in the t-table. 20 minus 2 is 18. The sig2 tail, this is our p-value. This is considered significant because this number right here, this is our p-value. This is less than alpha. This is less than 0.05, and so this would be considered a significant difference. And then standard error right here, 0.333. When we calculated estimated standard error earlier, we got 0.3 repeating, which is exactly what we got here. So this is nice. SPSS is giving us the exact same values that we got when we did the t-test by hand. And time really flies when you're having fun. For me, that was fun. So that is it for class today. So we will start off here next time talking about this stuff. We'll get a little bit more about the group projects next time as well. If anyone needs to stick around and talk to me, definitely feel free to. Or if anyone wants to make an appointment to talk about whatever, definitely feel free to stick around and to make an appointment or send me an email.